Hello and welcome to G Fun Facts Online. Imagine a world where the pitter-patter of raindrops on your roof does more than just lull you to sleep. Imagine a future where a downpour becomes a source of clean, renewable energy, powering our homes and devices. This isn't science fiction. It's the burgeoning reality of hydrovoltaics, a revolutionary field dedicated to generating electricity from water. Today, we're diving deep into the symphony of the skies to understand how science is turning every single raindrop into a note of clean energy. For centuries, we've used massive hydroelectric dams, but the subtle energy in one falling droplet has been almost completely ignored. The hydrovoltaic effect, a term coined only around 2018, is changing all of that. It's about generating electricity directly from the interaction between nanomaterials and water. So, how do we get electricity from a simple drop of water? The secret lies in a phenomenon that happens at a microscopic level, known as the electrical double layer, or EDL. The idea isn't new. It traces back to 1859, when a German physicist discovered that forcing water through a narrow pipe could generate a voltage. But modern science has taken this to a whole new level. When almost any solid material touches water, a subtle but crucial rearrangement of charges happens right at the interface. The material's surface gets a slight charge, and this attracts oppositely charged particles, or ions, from the water. These ions form a tightly bound, immobile layer. Just beyond this, a second, more diffuse layer of ions forms. Together, these two layers create the electrical double layer. The key to generating electricity is to disturb this layer. Any process that makes the ions in that outer mobile layer flow creates a net movement of charge, and that movement of charge is, by definition, an electrical current. Scientists use a few different mechanisms to do this. The first is the one discovered back in the 1800s, called the streaming potential. When water flows over a charged surface, it literally drags the mobile ions in that diffuse layer along with it. This flow of ions creates a voltage difference from one end of the material to the other, which can drive a current. Another method is through ion gradient diffusion. If you have a difference in ion concentration across a material, say because water is evaporating at one end, ions will naturally move from the high concentration area to the low concentration area. If the material has charged pores, it can selectively allow certain ions to pass through, creating a net flow of charge and a voltage. But the most important and powerful mechanism for modern raindrop harvesters is the triboelectric effect. You've experienced this yourself. It's just static electricity. It's what happens when certain materials become electrically charged after they touch and then separate. When a water droplet hits a specially designed surface, there's a transfer of electrons. Water tends to be a positive triboelectric material, meaning it happily gives up its electrons and becomes positively charged when it touches many polymers. As the droplet spreads out and then rolls away, this separation of charge creates a powerful electrical potential that we can harvest. To make any of this work, you need special materials. And this is where nanotechnology has become the ultimate catalyst. Materials engineered at the nanoscale have an incredibly high surface area to volume ratio. This means a tiny amount of material can present a huge interactive surface for water droplets, maximizing the effect. Researchers are working with a whole family of amazing nanomaterials. First up are carbon-based nanomaterials, like graphene and carbon nanotubes. Graphene, a single layer of carbon atoms in a honeycomb pattern, is a superstar. It's superconductive, incredibly strong, and has a massive surface area. By tweaking its surface chemistry, scientists can precisely control how it interacts with water to generate more electricity. Then you have materials like layered double hydroxides, or LDHs, which have a unique layered structure, perfect for generating electricity through ion diffusion. Even common metal oxides, like alumina and zinc oxide, are being used. For example, A generator made by coating a flexible film with nanoalumina can produce a voltage just from water migrating through its tiny, charged channels. And of course, there are polymers. Flexible polymers are crucial for creating practical, large-area devices. PVDF is a popular choice for its piezoelectric properties, meaning it generates a charge when deformed by a raindrop's impact. And PTFE, the stuff in your non-stick pans, is a champion in triboelectric devices because it loves to grab electrons and become negatively charged. Scientists are even looking at bio-based materials. In one experiment, a simple piece of wood with its natural microchannels was shown to generate a voltage as water evaporated from it. A key factor for many of these materials is their wettability. For triboelectric devices, you often want a super hydrophobic or water-repelling surface. This ensures the droplet rolls off quickly after impact, completing the contact and separation cycle efficiently so the device is ready for the next drop. Having the right material is only half the battle. The real genius is in the design of the devices that put these materials to work. The two dominant approaches are based on the piezoelectric and triboelectric effects. Let's start with piezoelectric harvesters. These devices capture the raw kinetic energy of the impact. Piezoelectric materials generate a charge when you apply mechanical stress. So when a raindrop smacks into a piezoelectric surface, the force deforms the material and creates a voltage. Early designs included simple cantilevers, a beam fixed at one end that vibrates when hit. A slightly better design is a bridge structure, fixed at both ends, which constrains the vibration in a more controlled way and generates a higher voltage. But a big problem was that much of the raindrop's energy is lost from splashing on a dry surface. To solve this, Italian researchers came up with a clever innovation, a cantilever with a tiny spoon-like structure at its tip. This spoon holds a permanent, tiny pool of water. When a new raindrop falls into the spoon, it hits a liquid surface instead of a solid one. This dramatically reduces splashing and increases the energy transferred to the piezoelectric element. It was a simple but brilliant fix. However, despite these innovations, piezoelectric harvesters generally suffer from very low efficiency, often converting less than 0.12% of a raindrop's kinetic energy. They are simple but not very powerful. This brings us to the real heavy hitters, triboelectric nanogenerators, or TENGs. Specifically, droplet-based TENGs have emerged as the most powerful and promising technology for raindrop energy. These devices use that contact and separation principle we talked about. A truly game-changing design is the field effect transistor-like structure, or FET-like structure. Now, a traditional FET in a computer chip uses a gate voltage to control the flow of current. In this new raindrop generator, the falling water droplet itself acts as the gate. Here's how it works. You have two electrodes. The bottom electrode might be a piece of glass coated with conductive indium tin oxide, or ITO, and then a layer of a dielectric friction material, like PTFE. The top electrode is a strip of aluminum placed on that surface. When a water droplet hits the surface, it spreads out and creates a conductive bridge between the top aluminum electrode and the bottom electrode. Because of the triboelectric effect, the PTFE surface and the water droplet exchange charge, creating a closed-loop circuit and causing a current to flow. Then, as the droplet rolls away, the connection is broken and the system resets, ready for the next drop. The results from this design are staggering. Researchers from the City University of Hong Kong demonstrated that a single 100 microliter droplet, that's about 2 drops from an eyedropper, falling from just 15 centimeters, could generate a voltage of over 140 volts. That was enough to momentarily light up 100 small LED bulbs. The secret was that continuous droplet impacts cause charge to build up and accumulate on the dielectric surface until it reaches saturation. This overcomes the low charge density that limited earlier designs, and the instantaneous power can be thousands of times higher than other methods. But TENGs had a huge Achilles heel: scalability. You'd think you could just connect a bunch of these units together in an array, like solar cells, to generate more power. But when scientists tried that, the total power output plummeted. The problem was something called unintended coupling capacitance. The electrodes of adjacent units were interfering with each other, causing the charge to leak away and cancel itself out. For a while, this seemed like a dead end for large-scale raindrop power. But recent breakthroughs have smashed through this barrier, moving these devices from lab curiosities toward practical power sources. One of the most important solutions came from a team led by Professor Zhong Li at Tsinghua University. They took inspiration from solar panels and designed what they call a bridge array generator. They realized the interference was caused by the large, continuous bottom electrode used in previous arrays. Their solution was brilliantly simple: break the bottom electrode into an array of smaller, separate sub-electrodes. They then connected these smaller electrodes in a way that made each raindrop powering unit electrically independent from its neighbors. This bridge reflux structure effectively isolated the units and eliminated that parasitic capacitance. The results were astounding. The peak power output of their bridge array generator was nearly 5 times higher than a conventional large-area Teng of the same size. They reached an impressive peak power density of 200 watts per square meter. This was a monumental step, providing a feasible blueprint for creating large, efficient raindrop harvesting panels for our roofs. As impressive as that is, another recent innovation might be even more elegant and practical. A team at Nanjing University developed a floating hydrovoltaic device. This design completely rethinks the generator by using the water body itself as a key component. Instead of a rigid, land-based device with a solid base and a metal bottom electrode, this generator is designed to float on a lake or reservoir. The device is just a thin, flexible dielectric film with a top electrode. The water it floats on acts as both the mechanical support and the bottom electrode. This nature-integrated design has incredible advantages. First, by getting rid of the rigid substrate and metal bottom electrode, the device's weight is cut by about 80% and its cost by around 50%. Second, the performance is fantastic. When a raindrop hits the floating film, the water underneath provides robust support for the impact, and the dissolved ions naturally present in the lake water act as effective charge carriers, allowing the water to function as a reliable electrode. This setup consistently achieves peak output voltages around 250 volts per droplet, matching the performance of much heavier and more expensive land-based models. It's also incredibly durable and scalable. The design maintains stable operation even in changing temperatures and when exposed to biofouling in the lake. The researchers even built a 0.3 square meter integrated device that successfully powered 50 LEDs at once. You could deploy these systems across vast water surfaces without occupying valuable land, perfectly complementing other renewables like solar and wind. Now, despite this incredible progress, the path to a world powered by raindrops is still strewn with challenges. We have to be realistic. The most obvious limitation is intermittency. It only rains some of the time, and the frequency and intensity are unpredictable. This means any practical raindrop energy system must be paired with efficient energy storage, like batteries or supercapacitors, to provide a steady supply of power during dry spells. Another hurdle is the average power output. While the instantaneous power from a single drop can be high, the average power over time is still relatively low. Current devices only capture a tiny fraction of the total kinetic energy available from rainfall. Improving this energy conversion efficiency is a top priority for researchers. Then there's durability and maintenance. Devices deployed outdoors have to withstand UV radiation, extreme temperatures, impacts from hail, and biological fouling. The long-term durability of these large-area films and electrodes is a critical engineering challenge. And finally, there's cost. The complexity of manufacturing large-area devices with nanomaterials is still a significant barrier. While innovations like the floating generator are drastically cutting costs, we still need to develop mass production techniques to make the technology economically viable on a commercial scale. Also, the high-voltage pulse DC output from these generators needs to be conditioned before it can be used by standard electronics or fed into a grid. So while powering entire cities with rain may still be a distant dream, the immediate applications for hydrovoltaic technology are both practical and transformative. The most promising application is in powering the vast networks of small, remote sensors that make up the Internet of Things, or IoT. Think of environmental monitoring systems for water quality, air pollution, or agriculture. These are often placed in remote, off-grid locations. Powering them with rainfall would eliminate the need for costly and difficult battery replacements. A floating generator could literally power a sensor that monitors the very body of water it's floating on. We can also imagine smart infrastructure. Smart windows that generate power when it rains. Umbrellas and raincoats that can charge your phone. The development of flexible, transparent hydrovoltaic cells opens the door to integrating power generation directly into everyday objects and building materials. Hydrovoltaic energy is also not meant to replace other renewables, but to complement them. Hybrid systems that combine hydrovoltaic panels with solar cells are a particularly exciting prospect. Such a device could harvest energy from sunlight on clear days and from rain during downpours, providing a much more consistent, all-weather power source. Researchers have already built integrated devices where a solar cell acts as the bottom electrode for a tangi, harvesting both types of energy. In regions with frequent and heavy rainfall, like the tropics, large-scale hydrovoltaic installations on rooftops or reservoirs could become a significant source of distributed clean power for local grids or off-grid communities, where decentralized energy is desperately needed. The journey of hydrovoltaics is a testament to our relentless quest for sustainable solutions. From a nearly 170-year-old physics observation to the sophisticated nanomaterials of today, we are steadily unlocking the power hidden within the water cycle. The challenge is immense, but the progress has been exponential. With each new material and every innovative design, we move closer to a future where the sound of rain is not just the sound of nature, but the sound of clean, renewable power being generated all around us. The symphony of the skies has begun, and we are finally learning to listen. Thanks for tuning in to Fun Facts Online.